All right, today we're going to talk about section 3.4. This is reduction of order, and we'll also, repeated roots, but we're also going to deal with reduction of order and see some similarities in there. So, when we solve our characteristic equation and do our discriminant, it's going to equal 0. So, if we have this, we can make our characteristic equation. And then we use our quadratic formula. A is 0. So everything is going to reduce. Treat it 2A down to there. Write this a little bit nicer. So whenever we make our R1 and our R2, our R1 is going to be, or excuse me, that's going to be both our R1 and R2. Whenever we do our Y's, our Y1 is something along the lines of the RT. Then our Y2 cannot equal the same thing. Because if it does, then our two solutions there are linearly dependent. They are a linear combination of each other. And so if we do our Vronsky, it's going to equal 0, which we cannot have. So actually, it's not even a linear combination. It's a simpler part of that. It's a constant multiple of one another. So that means our Y2 has to be in this form. Some function times Y1. So now we have to find that. So now using that, I'm going to rewrite it. I'm going to just write V, not V of T, just to save a little bit of effort here. And now let's take the derivative. Now we are going to have to do a product rule here. And then let's take our second derivative. And let me make this a little bit nicer. Now those two can combine together. And I'm going to rewrite a little bit. So there's what we have now. Now keep in mind that this is all going to solve our basic equation. And I'm going to clear this page. I'm going to make this B look a little bit nicer than that. My best effort. Now, for this to work, both Y1, when we take our first and second derivative and plug it in, has to equal 0. Same thing when we plug in our y2 with the first and second derivatives. So let's do that. And this is going to be a bit cumbersome. And this should be an r squared. I had that last one. I missed my. Oops, I had those. No, we're good. I have the r squared there. Just checking I have everything the way it's supposed to be. Okay. Plus b, and then times our y2 prime for b r e to the rt e plus c times r. And that is still going to all equal 0. And just double check, make sure I wrote those down correctly. Good. Okay, now notice that every single one of these has an e to the rt. So we can pull that out. And then we can regroup them based on having the double primes, the primes, and v's. Or v double prime, just going to be e the rt. RV prime is a 2r v double prime that has an a in it as well. It's going to be a 2r times a plus a b. And then just our v is going to have a 2, excuse me, an ar squared plus a br plus a c. And again, equal to 0. Now, based on what we did before, with that thing, if we plug in the r value we found, it's going to equal 0. That's what we did the whole quadratic for. We were setting that part equal to 0. So this is all gone. So now we just have to deal with the rest of it. Oops, sorry, this is no longer there. We factor that out. So now it simplifies. And we know what our r is. It's negative b over 2a. So whenever we start to plug stuff in, an a actually, what happens here? The 2 cancels the 2. The a cancels the a. And it's a minus b and a plus b. So that is all gone. That's all equal to 0. So our final thing that we're left with after we simplify is there. And we know that the e part is never going to be 0. We know it's a second order. So our a cannot be 0, or else it'd be a first order. So that's not 0. So that must be. So let's look at what happens. If we take an integral, that's going to be a constant. If we take another integral, and we use t as our variable here, there's our v. So whenever we do our y2, it's going to be v times y1, which is ct plus k times e to the rt, which we can then distribute to get down to here. Of course, we want the simplest form possible for our y1, y2. We want them to be simplest form of our fundamental set. We don't need any constants in this S work for any constant. So we can ignore those. And this part is redundant. It's already included in our y1. So we only need this portion here as our solution. Now, we do this again, another way of convincing you that this is not needed, that whenever we do our overall solution, C1 times Y1, C2 times Y2. If we write the whole thing out, and then distribute, we can then rewrite by grouping things together as you can see, that's just a constant and that's just a constant. So the two things that actually make our solution, that give us our fundamental set for our solution, are given there. So that's where we give just our normal way of doing it, but then we multiply a t in there in front. And we're going to see this later on, that if we would have three solutions, our next that are repeated, our next one's a t squared, and a t cubed, then a t to the fourth, then t to a fifth. And we're going to keep on just multiplying extra t's in front of there as we get more and more repetition. So we'll do an example here in a minute. Okay, so let's get a new page. Now, a reduction of order. We kind of saw it in that last example. And so we're going to look at our general setup. With our homogeneous second order linear. And just what we did, we know that y1 is a solution. So it's going to satisfy this equation. And then y2 is also a solution, but it's going to look like this. Now this is general solution. It doesn't have to be just the repeated ones. Since we know that y1 and y2 are a fundamental set, they're going to be linearly independent. So our v of t is going to be our y1 has to be multiplied by something other than a constant to get our y2. We don't know what that is. It could be anything, but they are always going to have this relationship. With our repeated ones, it's just a very simple one of v of t, just turns out to be a t. Just makes it nice. So we have all of our derivatives that we took before. And whenever we plug it in, we get down to this situation. And we solve this happily. So we're going to do the exact same thing we did before. And actually, let's just walk through it. We're going to use the same y2 prime. And I'm just going to do these just so that we don't have to worry about the of t. And then combining. Now let's plug that into our original equation up here. And again, I'm going to drop the of t's just to make it a little bit cleaner. So our y2 prime is this. I'm going to rewrite it a little bit. P times Q times that. And that's all going to equal 0. So doing what we did before, let's distribute and recombine in terms of our y double primes, v double prime and v prime, and just v's. So we only have one of those. Now our v prime, that's there. And then our these, we have those. Just like we did before, that whole thing, y1 is a solution, is going to equal 0. So that's all gone. So what we're left with is what I wrote on the other page. Now this is a second order equation because it has our v prime and our v double prime. However, if we do a little bit of adjusting, let's divide everything by y1. to get down to there. Now, let's rewrite our V's. Let's say V double prime is W prime. So V prime would just be W. And then we can take this entire thing, since our Y1 prime, and our P all depend on T's, that's some function of F, or some function of T. So we can call this whole thing just an F of T. So we have now reduced our second order equation down to a first order equation. And it's separable, it's homogeneous, and so it's a very, very easy one to solve. So we could then find W in terms of T. Now, of course, our next step, we've seen this before, is once we find W, we would have to integrate it again to find our V, because that's V prime, and then we can use that V to find our Y2. So it is a bit of an involved process, and you have to go through several steps of it. But it's not actually a hard process, and things simplify very nicely along the way. So let's try an example. Sure. Let's write our characteristic equation. And then this one we can factor. So our R is going to equal to order 2. All right, so we know that this is going to be repeated. So our Y1 is e to the 2t. Our Y2 is now t e to the 2t. So overall function is C1 e to the 2t plus C2 t e to the 2t. If we had initial conditions, we could then find our C1 and C2. But that's it. Now, our big thing here is recognizing that these are repeated. So we need this extra t multiplied in there. But since we found through our long process earlier that we do just multiply a t in there, and that's always going to work because we have just a very general solution or a very general setup, general equation. We don't have to go through that long process anymore. We know it's automatically going to get multiplied in there. So we can jump straight to our conclusion with our fundamental set. And now with our reduction of order, if they would ever give us one solution to a problem, we can then do what we did earlier and say that our Y2 is V times Y1. Take our first and second derivative, plug in, and then we're eventually solving for that V, which might include that reduction of order stuff, but it's a fairly straightforward process. So that is it for all of this.